Hi kids, and welcome to Allen High School. We are beginning a discussion primarily of solution chemistry. That's our real goal. But before we do that, we want to take a moment to review some of our key concepts that we have regarding pure liquids. Now, for liquid properties, some of the qualities of the liquids that we see are this. Liquids do sense intermolecular forces. Those are not bonding forces. Those are forces between two molecules. Now, they're much stronger than in gases, but they're still not quite as strong as they're in solids. So an example might be the hydrogen bonding that we would see between two water molecules. So this is an intramolecular within the molecule. The attraction between the partial positive on the hydrogen and that partial positive on the oxygen, because water is a polar molecule, that attraction is a hydrogen bond, and it's an example of an intermolecular force between the two water molecules. Now, in a liquid, especially compared to a gas, liquid molecules are very close together. That's why they're able to experience those stronger intermolecular forces, because as two molecules approach one another, just as, and you know it, if Denzel Washington got close enough to me, he would definitely experience some of those intermolecular forces I've talked about. So closeness facilitates the formation of those intermolecular forces. Now, liquid molecules, therefore, because they're already fairly close, are not able to be compressed or expand very much. They can a small amount, but negligible compared to what we saw with our gases and when we talked about our gas laws, where we really expanded gases into much larger volumes or compressed them into much tighter volumes. Imagine, if you would, when we did the Boyle's law with the syringe, your ability to really pull out that syringe or push in that syringe. You could move it pretty far with a gas. You can't do that very much with a liquid. Okay? Now, liquids are considered fluids. Gases are fluids too, because they have the ability to move. So the word fluid is a little bit broader than we tend to make it in our everyday language. But that fluidity, that relative ease with which molecules can slide past one another, allows molecules to diffuse easily. So diffusion is the just ability of molecules due to collisions to bounce around past one another. It's kind of a simplistic way of doing it. So if you can imagine putting a drop of food coloring, and try this at home, put a drop of food coloring into a glass of water and watch the color move throughout the water, that's the diffusion of the water. Now, liquids do take on the shape of their container. But unlike gases also take on the shape of the container. But here's a difference with your liquids. Your liquids do not take on the volume. They do not expand to fill the container. You put a gas in a container, it's not going to stay in one little corner of the container. It's going to spread out with as much room as it possibly can. But liquids don't do this. I don't know my Mimeo. You know, it's one of those days it's being a little jumpy today. Sorry about that. Okay. Now, liquids typically are less dense than their solid counterparts. In other words, liquid molecules are typically further apart. Man, I'm so sorry about that. They're typically further apart than they are in the solid. So if solids are packed tighter, they have more mass per volume. And if you have more mass per volume, if they're packed tighter, they're going to solids, so the density of the solid will typically be greater than the density of the liquid. Now, there's a key exception to that, and that exception is water. And I want to show you that in the next slide. And it's because of the hydrogen bonding crystalline structure of water in the ice. The extensive network of hydrogen bonds between molecules push the water molecules apart. And if you'll notice in here, do you see there's these big gaps of space? Now, when the intermolecular forces are broken, so if I'm going to go from the from the solid to the liquid phase, I'm going to take those intermolecular forces and I'm going to start breaking them. Now, it takes to break. It takes energy to break those intermolecular forces. That's why we have to add energy to melt ice. In other words, it's an endothermic process because it takes to break. So as those are breaking, because of this, pushed out kind of expanded network, as they break, water molecules can collapse into those gaps. And when they fill in those gaps, it actually becomes more dense. So the density, I meant that to be a D, the density of your liquid tends to be, for water, and that's unusual, greater than the density of the solid. Now, this is nice because if we have a lake and we have a bunch of little fish living in that lake, okay, that's Dr. Leggett's poor attempt to do fish with a mimeo that's bouncing all over the place. Okay, what happens is because ice is less dense, it's going to float, right? Because less dense things float on the top. So if you were going to stack density, do you remember a long time ago, it seems, we did that density column. This is a low density on the top, and this would be high density on the bottom. So because ice is less dense, it forms that protective layer on the surface of lakes and allows us to do fun things like skate. But not only that, it also is going to protect the sea and the algae and the plants and all of that from the cold. So that's an important part of that. Okay, so that is a quick little start, and we're going to continue this discussion in our next video. So until then, this is, of course, your very best chem teacher signing off.